Hello, my name is Robert Smith, and today we are going to look a little bit more at energy in chemical reactions and how we can read an equation and develop an equation from the information provided. So in this example, we are asked to calculate the change in internal energy at standard temperature and pressure, STP, for the following reaction. Well, the first thing we're going to want to recognize is what STP actually means. And STP means that it's at standard temperature and pressure. So the pressure at STP is going to be 1 atmosphere, 1 atm. And the temperature at ATP is 0 degrees Celsius, which is also equal to approximately 273 Kelvin. We're just going to keep it as whole numbers in this case, but you could also bring it to 273.15 Kelvin. So now that we have that, we need to think about what the term internal energy is. Well, we do have an internal energy term, and it's delta U. Delta U is going to be internal energy. And we have an equation to calculate our internal energy. And that equation is delta H, which is enthalpy, minus R, which is the gas constant, times T, temperature, times delta N, which is the change in moles. So the first thing we're going to want to do is look at the change in moles. And when it's asking for the change in moles, it's asking for the change in moles of a gas, specifically. So coming off to the side again, we can look at how many moles of gas we have in the product versus the reactant. In the product, we have 1 mole of CH4 and 2 moles of O2. So delta N is equal to 3 minus the moles of the reactant, which is only 1 mole of CO2 gas. So it's 3 minus 1, which gives us 2. So our delta N is going to be 2. It's relatively simple. Just make sure that you're always counting your moles of gas. This mole of liquid that we see here in water, we're going to ignore that when we calculate our delta N. So the next thing we're going to want to do is look at our formula and see if there's anything missing from it. Well, we're going to need delta H. Delta H is given to us as 890.4 kilojoules per mole, right over here. And R, our gas constant. Well, R is given specifically, R can be developed in many different ways depending on what kind of units you want to use. But in this case, we're going to use R is equal to 8.314 joules per Kelvin mole. And in looking at what kind of units we have otherwise, we see our delta H is in, up at the top here, is in kilojoules per mole. So either we're going to change our delta H into joules, or we're going to want to change our R into kilojoules. Either one is valid. I'm going to go ahead and change R into kilojoules, and all you do for that is simply move the decimal over 3 spaces to the left. So it's also equal to 8.314 times 10 to the minus 3 kilojoules per Kelvin mole. So now we have all the pieces that we need to solve our equation and find out what the internal energy, the change in internal energy, delta U, is. So we can find that delta U is going to equal delta H, which is 800 90.4 kilojoules per mole minus our gas constant, 8.314 times 10 to the minus 3 kilojoules per Kelvin mole times our temperature, 273 Kelvin, times our change in moles, which is just 2. When you do the arithmetic out, you will find that delta U is 885.9 kilojoules per mole. And that's the answer that we want. Some of you may be wondering why I left off the 0.15 on the temperature. And it's simply because when you're dealing with such small numbers, you have your 8.314 times 10 to the minus 3. So it's 0.008314 multiplied by this large number. Those two little decimals are not going to make that big of a difference. It's still going to be an exceedingly small number. In fact, in this case, it was less than 5. You see the difference between 890.4 and 885.9. That's 4.5. So if you factored in that extra 0.15, it would not have changed the value. It would have stayed 885.9 kilojoules per mole. Now, if we had more significant figures, it would have been much more relevant to leave in that 0.15 at the end of the 273. But otherwise, we just left it out this time. And that's all there is to it, to solving for the change in internal energy.